Anytime we're talking about a volume of air, specifically, we need to consider the different conditions in which air may be. Specifically, when we're talking about a clinical measurement of air or an air volume, we're talking about ATPS, BTPS, or STPD. Now you might be wondering, why are we talking about different conditions? If you think back to your basic sciences classes in high school, or maybe even in a chemistry class that you took here at the university when you were just a lowly freshman, you'll probably remember that unlike a liquid or a solid, a gas is extremely sensitive. Specifically, temperature and pressure can affect the volume of that air. Now that occurs also with a solid or a liquid, but at much more extreme temperatures and pressures. So a gas is actually very, very sensitive. Okay, and maybe the best example of this would be, let's say you blew up a balloon in a normal room, normal temperature, and then with that balloon, you put it outside in freezing cold temperatures, like below zero temperatures. Maybe you've had this experience before, but ask yourself, what would happen to that volume, that balloon volume, that volume of air? I've done that before, and as you might imagine, the balloon has substantially more give to it. It's shriveled. And so what actually is happening here is that volume of air is actually constricting or getting smaller. To begin our conversation today, I think I want to go back to this very simply. These gas laws, which I'm sure you've seen before. Charles' law and Boyle's law. Charles' law is probably the one that people can relate to the most. And basically it states that there is a direct relationship between a gas temperature and the volume of that gas, presuming that the pressure remains constant. Boyle's law is a little bit different. It states that there's an inverse relationship between the gas pressure and the volume of that gas, presuming that the temperature stays constant. So with respect to Charles' law, in the example I just gave, the temperature dropped from a standard living room to outside in freezing cold temperatures in winter, and therefore that volume of gas actually got smaller. So when we're talking about these different conditions, ATPS would be ambient condition. In the case of our example, it would be that living room. Or perhaps more to the point, here in a normal laboratory setting. So we're talking 20 to 23 degrees Celsius, which is approximately 70 to 75 degrees Fahrenheit. Normal humidity, nothing extreme. That's ATPS. BTPS is the temperature and pressure within the body, which is 37 degrees Celsius or 98.6 degrees Fahrenheit. So considerably more warm than an ATPS condition, which would be a temperature-controlled lab. Okay? Saturation is also very high. STPD is a little bit different. Standard temperature, pressure, dry. This is a standardized condition. It's not a situation that we can really imagine. It's no physical location. But it's a condition in which the temperature is completely zeroed out to 0 degrees Celsius and the pressure remains fixed at 760 mmHg. So why do we care about this? Well, given what we just talked about with Charles' law, about how gas volumes can change, it's important to consider what happens when we breathe a volume of air from inside our body, BTPS, our lungs, out into the atmosphere, ambient temperature pressure saturated, or ATPS. And so if we're thinking about this according to Charles' law, as you might imagine, when we change this, when we breathe air out of our lungs, into a spirometer, which is obviously outside of our body, it goes from ATPS to BTPS, and therefore things are going to change. But first of all, we've got to realize that all volumes of gas are measured via ATPS, because a spirometer, an instrument, that would be in a lab outside of our body. But it should make sense to you that as we go from ATPS to BTPS, so as a volume of gas is moving from our lungs to outside of our body, that volume is going to be smaller. But obviously if we're calculating oxygen consumption or any other clinical variable, we want to know what that volume is in BTPS. So that volume will be measured in ATPS by the spirometer, but we'll need to apply a correction factor to get it into BTPS terms to reflect that was a volume that was expired from our body. And so actually, that error will get bigger once we apply that correction factor. Now, how much bigger? That depends on the temperature difference and pressure difference between the ambient condition and our body, which remains relatively fixed. And you can see we have the opposite, which is true when we are converting from ATPS to STPD. In class, we talked about the different lung volumes, albeit very briefly. We talked about tidal volume, which is the amount of air per breath, a normal breath. We talked about IRV, which goes from the end of a normal inspiration to forcibly inspiring till you can't inspire anymore. And ERV, which is at the end of a normal expiration and then continuing to force out air until you can no longer force out air and you have to take a breath in. And we also talked about residual volume, which is the volume which remains in the lungs following maximal expiration. These four volumes are clinically important, and we measure these. In fact, IRV, tidal volume, and ERV can be combined to become vital capacity, or VC, which is one of the more clinically important capacities. Now, there are other capacities, as you see, and they are made up of combinations of volumes. You need to know what these volumes are and these capacities, which are reflected in this PowerPoint. This is the output of an FVC test, or forced vital capacity. So this is where we will clinically force out the air. And as you'll see in the upcoming example, an individual breathes into a spirometer with nose clips, so no air escapes, normally until the conditions are right, and the administrator typically puts up a finger, and that person will take a breath in as far as they possibly can go, so getting their IRV, and then they will forcibly expire all of that air, as you can see on that downslope there, until they can no longer expire air. And so they've expired their IRV, their tidal volume, and their ERV, which makes up their vital capacity, or in this case, forced vital capacity. Now, when that occurs, we're not just interested in how much air they can expire, but rather the rate at which they can do it. And so a second variable becomes important here, and that is FEV1. In other words, the first second's worth of volume of that FVC test. So when you take that FVC test and you're expiring your air and you're breathing out, and you want to breathe in, well, that might last 4 or 5 seconds, but the first second of that is your FEV1. So from a clinical standpoint, we want to know the ratio FEV1 divided by FVC. Now this should be greater than 70%, or 0.70. In other words, of all that air that you forcibly expire out of your lungs following a maximal inspiration, over 70% should be expired during that first second of that FVC test. If it's not, it indicates that there is some sort of large airway obstruction, or something is keeping that air from coming out at the rate at which it should. What this directly tells us, as I just mentioned, is that there is an obstruction. But it indirectly also tells us that exercise performance could be limited simply by our pulmonary function. So it doesn't directly tell us that there's a limitation of exercise, but indirectly, when someone typically has a blockage, think asthma or even a cracked rib or emphysema, well, that's probably going to influence how they exercise. This is an output of an MVV test, or maximal voluntary ventilation. And you can see here all the individual's doing is purposefully hyperventilating in and out as hard and as fast as they can. It actually occurs for a period of 12 seconds. And as we'll talk about later, that actually has ramifications in that MVV is, well, even though it's in terms of liters per minute, we're only collecting data for 12 seconds. And then we assume that the other 48 seconds are essentially at the same rate of that first 12 seconds, which is a huge assumption to make. And therefore, this is a theoretical variable. But it also has clinical significance. So as I just mentioned, typically we do this for 12 seconds, and then you multiply by 5 to make 60 seconds, or for 15 seconds, and then you multiply by 4 to get 60 seconds. Either one, we do it by 12 seconds. An MVV is purposeful hyperventilation while sitting down, and you'll see that in just a moment. And where this is really important is how it compares to VE max. Now VE max, as we talked about in class, is minute ventilation during maximal intensity exercise. So here's the thing. if during maximal intensity exercise, you have to get off the treadmill, and your VE max, the amount of air you were taking in and out of your lungs when you stopped exercising because you couldn't push yourself anymore, was 150 liters per minute. If you compare that to a person's MVV, sitting down, that means forcibly expiring air in and out of their lungs, let's say that was 205 liters per minute, well then clearly something else occurred that forced you to stop exercising, because according to that test, you had another 55 liters per minute that the lungs could pump in and out. And so that's what we say here when we say MVV should exceed VE max by 35%. Here are two hypothetical examples for you with these ratios. As you can see with FEV1 and FVC, we're assuming that their FVC was 4.5 liters and their FEV1 was 4 liters. That equals 0.888 or 88%. In other words, 88.8% of their FVC was expired within the first second of that test. And because that's well above 70%, there is no indication of some large airway obstruction. With MVV over VE max, we're actually going to use the numbers I just suggested here, which is at VE max, it's the maximal amount of air being pumped in and out of the lungs during maximal intensity exercise when the person had to get off the treadmill or whatever because they could not possibly push themselves any further. That's 150 liters per minute. This is all hypothetical. But when they did the MVV test sitting down using a spirometer, it was substantially higher than that. That comes out to be 1.366 or 136%. Or said a different way, MVV was approximately 36% greater than VE max, which suggests directly that the lungs did not limit exercise performance. So that's a direct indication of whether pulmonary function is a limiting factor. Whereas FEV1 over FVC directly tells us there's an obstruction, and then indirectly tells us that the lungs may influence exercise performance.
Go.
All right, so we're going to do an FVC measure. So what I'm going to have you do is you're going to put the spirometer in your mouth, you're going to breathe normally, and then when I tell you to go, you're going to breathe in, take a deep breath, and then you're going to release it as hard and as fast as you can. You need to go for 6 seconds, so I'll tell you when to stop. Sound good? Okay.
This is FVC trial 1.
Go. Deep breath in. Good. Good job. Keep going. Keep breathing. Keep going. Good. Good job.
Oh.
So within this FVC measure, we also get FEV1 as well.
This will be FVC trial 2.
Go. Breath in. Okay, faster, faster. Keep going. Keep breathing. Keep breathing. Good. Good job. All right, so we're going to be doing an MVV measure today. So what I'm going to have you do is you'll be wearing the nose clips. You'll be breathing in the spirometer naturally, but when I tell you to go, you're going to basically be hyperventilating for 12 seconds. So really going the in and out. And again, that has to go to 12 seconds. All right? Okay.
This will be MVV trial 1.
Go. Good. Keep going. Good. Really some deep, strong breaths. Good. Keep going. A little faster. There you go. Good job. All the way to 12 seconds. Good.
This will be MVV trial 2.
Go. Good. Okay, a little faster. Keep going. Good. There you go. Okay, you're halfway done. Keep it up. Good job.
So we have only one participant today. She's female. She's 20 years old. She weighs 47.3 kilograms, and she is 150.5 centimeters tall. What you just observed was an FVC test and an MVV test. During the FVC test, when we get the data afterwards, we also get data for FEV1, because that is actually the first second of our FVC test, or volume. For trial 1, FVC, our participant was 3.45 liters. That means after a maximal inspiration, the total volume she could force out was 3.45 liters. And the first second of that 3.45 liters was 3.20 liters, okay? Which simply means that after a second of that FVC test, the volume that was forced out was the difference, 0.25 liters. For trial 2 FVC test, a little bit higher, 3.53 liters, but the FEV1 within the first second was actually lower than trial 1 at 3.07 liters. You also observed her do 2 MVV tests. For trial 1, that came out to be 89.8 liters per minute and 89.0 liters per minute. Now, something here we need to preface. With the FVC test, that's just a volume. It doesn't matter how long it lasts, although the FEV1 is the first second of that FVC. MVV is different. As shown in your lecture, and as I just showed you here with our PowerPoint, when we do MVV, we do it for a period of 12 seconds, and then we extrapolate that volume to a minute. So in other words, the volume which is measured, we essentially then multiply that by 5, because 12 times 5 is 60 seconds, or a minute. And this is maximal voluntary ventilation, so it's in liters per minute. So this volume here for trial 1, and this volume here is trial 2, was the volume that we measured in there during the MVV test times 5. Came out to be this and this. As you might imagine, there are some inherent limitations with MVV, because we are assuming the volume we measured for seconds 1 through 12 is the same as the volume that we would measure for 13 through 24 and so on and so forth until 60. But we have to wonder is whether or not that volume for those next 12-second increments will be the same as it was for the first 12 seconds. There's some debate as to whether or not that would be the case, namely with respiratory muscle fatigue, something we touched on in last week's lectures. So that's something to consider with MVV, and that's why when we're talking about MVV, it is actually a hypothetical measure. It's a hypothetical measure because we only measure 12 seconds of that 60-second value. But regardless, the outcome variable is in liters per minute. So it's always kind of got an asterisk next to it. In contrast, the FVC volume, we measured that, we're sure about it, there should be no doubt that that's what the volume is. On your data sheet, you'll see under forced vital capacity and under FEV1, there is a percent predicted for each trial. Very simply, to get the percent predicted, what you'll do is you'll take the trial value and then divide it by the predicted value. And that's going to give you a percentage. For the FVC, the predicted value is 3.18 liters. And for FEV 1.0, the predicted value was 2.82 liters. That's based on a person's gender and on their height and to an extent upon their weight. So that is pre-calculated before any of the measurements. So to get the percent predicted for trial number 1 for FVC, you would simply take the trial, 3.45 liters, and divide it by 3.18 liters. And you're going to get then 1 point something something, or in a percentage, it'll be well over 100%. It doesn't have to be over 100%, but in this case, and in both of these cases, it will be. So we can meaningfully say for FVC and for FEV1, our participant exceeded the prediction value.